continuing module 5. This is module 5b, floating point. We have module 5a on integer. We are finishing module 5b today. And I have your quiz 4 graded and it's here. At the end of the class, I'll give it to you. Quick review of what we talked about. We talked about the floating point representation, which is.
Do you ask a question about the project?
Sure.
I wasn't sure about, like, did you want us to have an input-output system so they input the array? Okay, so
You can
the graders actually input in the array for us.
And with the syscall, I actually created something to print it, but that is not necessary either.
Okay.
Right? So it's just, you can hard code that in the memory. The part that it actually goes to the memory, you can assume that's done.
Okay. And do you want us to handle, like, error handling on it? So if, like, the arrays don't match or anything like that?
No,
they don't
we
match
just,
like the
so
end
we
value?
just assume that the arrays match. Yeah.
Okay.
Yes, we don't have to check if arrays match or not. Yeah. And even if you don't,
It shoots something out, but I was like, yeah, that
it's gonna. It depends on what you put for the n.
Yeah.
Which is the size of the array. It keeps the smaller one.
Yeah.
Anything. So.
Okay,
So
cool.
you're not gonna have any problem. But yeah, you're gonna have the same size. Any other question about the project? So we talked about floating point. We mentioned that this is the same scientific notation that we had in decimal, and then we talked about the standard for it because we can show floating point numbers in different ways. From the hardware point of view, we want to have a standard, so we design a hardware such that it follows the standard. And we talked about the single precision floating point. It has sign, bit, exponent field, and fraction or mantissa. And then we mentioned that we have significant, which is 1 point fraction, but because that's a known information, we don't use a memory space for that 1, and we just assume that it is there, and that is called significant. And then we have some example of the conversion. I can ask these types of questions in the quiz and the exam. And yeah, this was one example, then we had another example, and obviously going from hexadecimal to floating point, that's another type of question you can have. You should be familiar with the fields that we have, the 3 fields. We talked about the double precision floating point and exceptions. We had a table of exceptions for overflow, infinity, not a number, and so on. And discuss the range of the numbers that we can cover by the float and single precision double precision floating point presentations, and we did talk about the arithmetic. So we talked about the addition before. I'm gonna go over the algorithm one more time quickly, and then we continue from there. Okay, so we told you that we can have questions like this, and I can give you 2 different numbers and a specific bit for precision. So in this case, we have 4-bit precision, and what we needed to do was, the first step was going to the binary representation. So in this case, we're not making it overcomplicated for ourselves. We just simply make a binary and work with the binary number. You don't have to go to 32-bit floating point or 64-bit floating point, which is 4 bits, right? So when we have 0.5, this is going to be the binary representation for 0.5, and this is the binary representation for 0.4375. And now we have both of these guys this way. The next step was normalizing them, because we always normalize the number to find the exponent for each number. So when we normalize them, we just have a single 1 on the left side of the binary point, and every time that we shift it left once, we decrease the exponent. When we shift right, we increase the exponent. So this number 0.1 is equal to 1.000, and we have 3 zeros here because we have a 4-bit precision number, and we have exponent -1 because we shifted left once. In this case, we shift left twice to get a normalized number, and exponent is decreased 2 times. It's going to be 2 to the -2, and this is the 4-bit number that we get, 1.11, and an extra 0 here for the 4-bit. Now, the first step was comparing the exponents of the 2 numbers and shifting the smaller number to the right until they have the same exponent. Okay, so this is the smaller number, and when I say smaller number, ignore the sign. Someone asked this question last session, and that was a good question. So smaller number, just ignore the sign for here. This is the smaller number, because 2 to the -1, sorry, 2 to the -2 is the smaller number, regardless of the sign. This is a coincidence that it's a negative number here. So we shifted right once, and when we shift right once, we get this number, 0.111, and now the exponents are equal. When the exponents are equal, we can go ahead with the subtraction and addition of the significance. Here we want to add two numbers. One of them is positive, the other one is negative. So it's equivalent to subtracting these two numbers, right? So when we do the subtraction, it's a simple subtraction. Here you can completely ignore the final point and go ahead with the subtraction. But because these numbers are smaller numbers, again, this was a question that was asked last week, and I give an answer to class 2. This is number 8, and this is number 7. So you can just convert them to decimal. It's really hard for you to do it, and then go back to the binary representation. But subtraction is actually easy too. It's a simple subtraction that we have. So when we do the subtraction, the number that we get is 0.001 to 2 to the -1. Now the next step is normalizing the sum. When you normalize it, you have to shift it left or right until we have a single 1 on the left side of the final point. We have to shift it 3 times in this case to get this number, and every time we decrease the exponent, so we get 2 to the -4. Okay? We have to check if we have an overflow and an underflow. To find the overflow and underflow based on the table, if we have the exponent, but here what I mean is the biased exponent that has 127 in it. If that exponent is between 0 and 254, then we don't have an overflow. To find that, we have to add the bias to this exponent that we have here. This is an unbiased exponent. When we add the bias, we get 123, which is the number that is going to sit in the exponent field of the single precision floating point number. Okay. So this number is 123. It's between 1 and 254. I correct myself. We keep 0 for other cases. We have that in that table. So if the number is between 1 and 254 and inclusive, including 1 and including 254, then we don't have an overflow. So we don't have to activate any exceptions. Okay? So we're good. Go to the next step. The next step is rounding the significant to the appropriate number of bits. This is the case that you don't see here, and that's the case that we're going to talk about today. One of the reasons I went back to cover this is because of this box that you see here, and that's the step that we're going to talk about today. In this case, you don't really need it because it's already 4 bits. But what if it was 1.0001? Right after doing all those conversions, because you have 4 bits, you have to do something about that extra bit that you can't show in your representations because of the bit limitations. So that's when we do the rounding. Okay, what is the policy for rounding such numbers in floating point representation? In this case, we don't need it because it's already 4 bits, and we're good. And then we check if it's still normalized, which in this case it is normalized, and we're done. Okay, and then we have the number. The result is 0.0625, which is the correct number. Any questions?
Professor, you said that we don't consider the sign.
You don't consider the sign? Yeah.
In the previous example. So,
Yeah.
what if we are adding -0.5 and 0.4375? Which one is this?
So this is the thing that you have to. So we check the sign at the beginning, right? And if we have a number that is signed and a number that is not signed, that's where we decide whether we want to do a subtraction or an addition. Okay, so there is somewhere in the hardware that right in the beginning checks the signs of the numbers and decide whether I have to do a subtraction or an addition. That's it. Okay, so if it was a case where the example that you said was -0.5 and positive something, right?
Positive 0.4375.
So this was a case that this was positive and this was negative, right? So you have to do the subtraction. So this you have to subtract this from this. So you just subtract the negative number from the positive number. And if it's both of them are negative, you know you do an addition, but you know that these are negatives at the end, make them negative. Right? So what we do with the sign is decided at the beginning of the operation. What is actually happening in the code is simply an addition or subtraction. Right? We deal with the sign at the beginning of the code. Yeah, so one more time, if this one was negative, this one was positive, you have to just subtract 0.5 from 0.4, and obviously your answer is going to be negative. Any other questions? Perfect. So this was the hardware, we talked about it a little bit. You see it's a complex hardware, we have two small integer ALUs. So something that a lot of people get confused a little bit. They think that, you know, when we say floating point, there is some specific arithmetic that is happening there that is floating point arithmetic, floating point multiplier, right? It is, but reality is that we just do some additions, subtractions in integer, and then we have some control circuitry, some shift left, shift right rounding, checking the signs, but the actual math is also a small ALU that is responsible for doing an addition. Is basically doing an integer add or subtraction, and then we have a big ALU which is responsible for, again, you know, the significant, the fraction part. So in a single precision floating point, we have 23 bits plus the significand is going to be 24 bits. So this ALU is a 24-bit ALU, and then we have an 8-bit ALU here. But then you can see the entire circuitry around the two, the rounding, and so on, the control circuitry that you can see here. So in terms of the hardware utilization, in terms of the area occupation of the chip, in terms of the power dissipation, floating point operations are significantly more power consuming and, you know, area consuming compared to integer operations. So that accuracy that we're getting with floating point numbers is not achieved without any costs. The trade-off is power consumption, speed, area occupation. Now the next example, which we didn't cover last time, is a multiplication. So we do have another flowchart for multiplication, as you can see here. We are working with the same two numbers, so obviously the first step, you already know what it is. We convert it to binary, we still have 4-bit precision, so this is the number that we get, as you can see here. Now the first step is adding the biased exponents of two numbers. The biased exponents of two numbers. And then subtract the bias from the sum to get the new biased exponent. So these are the terms that you need to know. If we have an unbiased exponent, this is what you're seeing here, -1, -2. When you want to have a bias exponent, you have to add the bias to it, and bias is 127. So you add bias to both of these numbers, and then you subtract it by 127 to get the bias number. Because you're adding two biases, you just take one of them out. So this is what's going to happen. You can, in the unbiased case, we could have -1 plus -2 is equal to -3. If we want to have bias, we have to add the bias of 127 to this one, and again another 127 to this one, and take out one of them to have a bias exponent. So your end result is going to be 124. Another way of doing it was simply adding these two exponents and adding a bias to it. You would get 124 as well. Okay, so why do I say that you have to do these stuff? From our point of view as human, when we're solving these, it's very simple. You just subtract these two and add 124. It's because what is actually happening in hardware, right? We add the biases, we subtract the biases. These are the things that it works with, because what hardware has access to is bias exponents. So in a single precision floating point representation, the numbers that you're getting as inputs are already biased. But that 8-bit exponent is the bias exponent, and that's why in reality the hardware works with bias exponents and then take the bias out. So this step doesn't happen in hardware because all the exponents that we have are already biased. So 124, we add the exponents, and then we have to multiply the significance. Okay. So when you multiply the significance, again, we don't care about the sign at this point. Sign is handled separately. So everything that we're doing here is unsigned numbers. We have number of 1.000 and 1.110. So we have two 4-bit numbers. When we do the multiplication, we need 8 bits. And as we know with the decimal case, when you have a decimal number that has n bits on the left side of the number and n bits on the right side, if you multiply these two numbers, you need to have 2 n bits on the left side and 2 n bits on the right side, which is the case here as well. So we have 1 bit, we multiply these two, we need 2 bits on the left side. And we have 2 3 bits here, on the right side we're going to need 6 bits. Together it's going to be 8 bits, and that's something that we know. When we multiply m with a number with m bits and another number with n bits, the number of bits we need to for the result of the multiplication is m plus n. Okay, so you do the multiplication. It's a simple case here, it's just 1, so we already know what the result is. And when you do this, you get rid of the extra bits that we have. On the left side, we get rid of the 0, and on the right side, we get rid of the other zeros that we have, and we get the 4-bit number 1.110. Okay, so we multiply the significance as well. We have to normalize it in the next step, but it's already normalized. We kind of normalize it here, but just showing it here. So it's not accurate to say it was already normalized. We kind of did the normalization here, okay, ourselves. So do we have an overflow? No, because the exponent is 124, the bias exponent, which is between 1 and 254. So we don't have any underlying overflow, no exception needed. Then we round the significance to appropriate number of bits. The next step, which in this case we don't need to do, it's already rounded. We have 4 bits, 1.110. The exponent, we know that it's already 2 to the negative 3, so we're good. And this is still normalized. But then at the end, we have to deal with the sign, right? At the beginning, we get these two sign numbers and decide whether the product is going to be negative or positive. But after that point, you go with positive numbers. You do go ahead with the multiplication, you're done. At the end, we know that these were, one of them was positive, the other one was negative. So we add the sign, change the sign to 1. Okay? So it's going to be a negative number, as you can see here. So these are the steps you need to take to complete the floating point multiplication. So this is the hardware for floating point multiplication. We have exponents added in a block like this. And then we have an XOR gate. If you remember, XOR could handle the sign. So we have an XOR bit. The output of the XOR is going to sit in this output sign bit. And we have the exponent addition. We multiply the mantissa here, or significance. So we have a 24-bit multiplier. After doing the multiplication, in some cases we have to normalize it. When we normalize it, the exponent needs to change, right? So you add the exponents here, and you come to this point. Depending on how many shifts you have to make to left or right to normalize this, you're gonna update the exponent. So we have an exponent update block as well, which defines what the exponent is. So the hardware is a little bit more straightforward than floating point addition. Just a little bit. Okay. But in reality, it's going to be a little bit more power consuming because we have a multiplier here. In the floating point addition case, we didn't need a multiplier. We could do the computation by just 2 additions and subtractors. Any questions? Now let's talk about rounding. Okay. So rounding is, just for the fun of it, in 2019, I had an interview with AMD in Orlando. There was a group, the R&D for GPU, architecting GPU, and power consumption. So it was power group. We were to design GPUs that are very power efficient. In the interview, I had like a 2-day interview with them, and I had to talk with different people. So in 2 of those discussions that I had with 2 different managers, one of them was a manager, the other one was an engineer. They actually ask about how you round a floating point number, right? So because in my resume at this time, I took the course that you are taking now, and I was fortunate enough to have a better professor than myself. So they forced us to do very log coding. So in my resume, I had floating point implementation, like floating point implementation of addition, multiplication, and so on. So they asked me, okay, go ahead and explain how you do the floating point, and how did you do the rounding? Like this is one of those things that hardware designers, if you have to actually design the floating point yourself, it's such a pain to do, right? So a lot of people ask about how you did it, how did you implement it, and so on. So you need to know about it, and also it's a very common question that you get in a lot of interviews, depending on where you go. Job interviews, I mean. Like this is one of those lower hanging fruits that if they don't know how to ask from you when you go to an interview, they say, okay, how do you do floating point rounding? Like just in case. And this is mostly companies that, like, as I said, AMD, Intel, if you want to end up working in one of these companies that develop computer architectures and this kind of hardware, it's an easy question to ask. So it's a good thing to know. Just a fun fact about rounding. So now let's talk about rounding. There are different mechanisms that you can do rounding. One is truncation. Truncation, as it's clear from the name, we just ignore the extra bits, okay? As if we don't have them. We have the round toward positive infinity or round up. So you just make it a bigger number. We have round down, just make it a smaller number. And then we have, this is the confusing case, round to nearest ties to even. Okay, so you round to nearest, you're familiar with that one. But in case of a tie, we round it such that the least significant bit that we can show is an even bit. Okay, now let's see how it works. So I have a table here. Start from the first one. Let's say I have number, this is decimal, and we're familiar with that. We have 3-digit precision, so we can have two digits on the right side of the decimal point. It's a normalized number. So it's let's say we have number 1.4586. So 86 are the numbers that we can't show. Okay, and let's see how we do the round. If we truncate it, we just ignore these 2 digits. Done, gone, don't care about it. If we round down, we just, again, it's similar to, in this case, it's similar to getting rid of these 2 numbers. In a negative number, it's a different case. If I had a negative number, a negative 1 point, imagine this is negative 1, negative 1.4586, that would have changed to a negative 1.46. Right? That becomes a smaller. And positive is that, but you always go to the negative infinity. Okay? In positive case, round down and truncate looks like they're similar. Then we have round up, which we get this 86 here, but we just added 1 to the least significant digit that I have, and this becomes 1.46. And if I have round to nearest, this 1.4586, it can be either round to 1.46 or 1.45. This number is actually closer to 1.46, so it's going to be round to 1.46. Bad we know, okay? Straightforward. It's closer to 1.46, round it to 1.46. Now there's a case that we have a tie, okay? So this case is what we can see here. It's 1.4550. Okay, so when we have a 50, it's in the middle point, so we can't really see if it's closer to 1.45 or 1.46. Okay, in case of round to nearest ties to even, it says if it ties, then we change this bit that we can show to an even number. So this can either become 1.45 or 1.46. Because it's a tie, it's going to be rounded to 1.46. Okay. Now we have a case like this, which is 1.4650, which this number is already even. Okay. This is another tie. This number can either be 1.46 or 1.47, but because we want to round it to an even number, this also will be 1.46. That we know, okay? It is common sense. We've been living with decimal numbers. It's easy to understand, okay? So exactly the same thing happens in binary with a small change, and right there for no reason it becomes complex. I don't know why, but let's see. So it's a binary representation, right? We have 1 point, let's say we have 1.1001. If we want to truncate it, we get rid of it, we have 3-bit precision. If we want to round down, then again it's getting rid of these 2 bits, we get 1.10. If we want to round up, we have 1.1001, but we change this bit because we want to round it up to 1. Now we're going to get 1.11. Okay? Round to nearest. Round to nearest, if I have a number like this, 1.1001, this is closer to 1.10, so we're going to round to 1.10. Now, what is the tie case for a binary number? So this is a little bit strange, so let me just put it here so you can see. In this case, we have 2 bits, right? So with 2 bits, we can have numbers 0. We can have numbers 0, 0, 0, 1, 1, 0, and 1, 1, right? So this doesn't have that middle point that we got with 50, right? So they consider this combination 1 point and a bunch of zeros, depending on how many numbers we have. If we have 3 bits, it could be 1.00. If we had 4 bits, 1.000 all the way. So every time that we have 1 and a bunch of zeros, that is considered as a tie, right? Although we think that this is not a tie, this is more closer to the next bit, but it's not. It's considered as a tie case, okay? So now here we have a tie, because we have a 1 and a 0. So it's 1.1010. Okay, this is a tie. Now because it's a tie, we round the bit such that we get an even number, an even bit here. We happen to have 0 here, so we're good, and this is going to change to 1.10. Now, if we had 1.1110, okay, so this 10 is a tie again. Now, because this is a 1, we add a 1 to it to make it even. Okay? So when we add a 1 to this number, this is what we get 10.00. But because we have 3 bits, we can't show the last 0. I just included that 0 so you can visualize it and what is happening. Okay? So a common question that people usually ask when it gets to this point is that why didn't you change it to 1.10 and add the 1? And that's not even an option, right? The possible things that when you want to round this, these number, you should either add it with 0 or 1. You can't subtract anything with it. This is not how we work with rounding, right? We don't do the same thing here. We don't say 1.45, why didn't it go to 1.44? It's a common sense for us. We don't have subtraction here. Your options are either adding a 0 to it or adding a 1. Okay? So when you add a 1, this is the rounded number you get. Ignore the last bit here. I just have it there for you so you can see that is the result. Because we have 3 bits, we don't have the last 0. Okay? So far, any questions? Now let's deal with the 3 bits. What happens in IEEE 754 floating point representation? Okay, so we have In algebraic representation, our significand has 24 bits. We have 23 bits of fraction. Okay, so what we get is 1 point, the fraction. Now, to deal with rounding, we add 3 extra bits to the fraction. The first one is called guard bit, or G. Then the other one is the round bit, an R. And then we have a sticky bit, which is called S. Okay, so we add 3 bits to the fraction now. And they are simply working. The guard and round bits are simply adding some digits, some binary, some bits, such that we can deal with the rounding. Because the 23 bits, the last bit, the least significant bit in mantissa or fraction, that's the bit that should be normalized. In order to that's the bit that should be rounded. In order to use rounding, we have to have some extra bits to work with. These are the 3 extra bits that we have. Guard and round are simply 2 bits that we add. Sticky is a little bit different. It's also a bit, but when it becomes 1 for any reason, and you can see some example, because we do shift down right, the first time it becomes 1, it's going to stick to 1. So no matter what you shift, this number is not going to change. It's going to remain 1. That's why it's called a sticky bit. Okay. Now, maybe with some, as always, I think with some examples we can learn it better. We have 2 numbers. I already put them in the floating point representation. One is, this is the sign bit, we have the exponent field, and we have the fraction field. And then we add 3 bits GRS. Okay, these are the bits added to the floating point representation. Now we want to do an addition, and we have this flowchart before. This is nothing new. Again, at the beginning of the class, we went over this already, so we know how addition works. The first thing we need to do is we need to compare the exponents and shift the number, the smaller number, to right until the exponents are equal. So if we compare these 2 numbers, we can see that this is the smaller number. This exponent is larger than the other exponent. Okay, exponent is the larger. We get that one, and this is 5. We have 0 here. So now, if we do the subtraction of the exponents, it means that we have to shift the fraction right 5 times, so it's 1, 0, 1, to get the same exponent. Okay? Now let's start shifting the fraction right 5 times. We do it the first time, the 1 is moved to this one, and so on. Everything is moved right, and we add the exponent. Okay? We shift it another time, the exponent is 1, 0, and everything is shifted right. This one goes here, this one goes here, and so on. We shift the third time, and everything is normal again. We move 1 to this point, the sticky bit. This 1 here, 0 here, 1, 1, and so on. Now, for the first time, sticky bit has become 1. After this point, it doesn't matter what kind of shift we are making. Sticky bit is going to remain 1, no matter what. Okay, so now let's see how it works. Then this is the 4th shift. We have 1, 1 here, still it's not equal. So we have the 4th shift. Here, sticky bit remains 1, but you can't really see it, right? Because if I simply shift it as 2, I'm going to get a 1 here. But the reality is that the sticky doesn't care what is happening here. It is going to remain 1. So we have a 1 here, 0 goes here, shift, and so on, exponent is added. Now let's deal with the last shift. The last shift, if a sticky wasn't a sticky, if it was like guard around bits, this was supposed to become 0, but it is not becoming 0. Because sticky, when it becomes 1, it remains 1. Okay? And now we shift everything, and now the exponents are equal. So can you guess what is a sticky doing by keeping that 1? What is the point of having something like this? It's a hard thing to guess, so I give you the answer. this is representing all the ones we are losing in the shift process. So then the sticky bit is telling me, okay, I am losing ones by shifting right. I should do something about it. So if I see a 1, if I don't see any ones, if I'm only losing zeros, cool, I keep it 0. But even if I lose one single 1 in the process of shifting right, then to represent that 1, I keep sticky as bit 1. Okay? This sticky bit is representing all the ones that we lose in the process of shifting right. Okay? So now we have the exponents are equal, we can add the significance. So these are the two numbers we get after shifting them. So this is the first number after all the shifts. And GRS, you look at this, we are getting 1, 1, 1. Okay? So this is 1, 1, 1. Now we can add the significance. Okay, adding the significance is actually pretty straightforward in this case because we're just adding ones and zeros. And this is what you get. 1, 1, 1, and then we normalize the sum. It is already normalized, so the significant doesn't change that much. This number is already normalized. If it wasn't normalized, then again we have to shift it left and right. And this is the number we're getting, 1 point, bunch of ones here. There's no overflow and underflow because, okay, I won't show this one. There's no overflow or underflow because this number is between 1 and 254. So we're good. Now we want to do the rounding one more time. Okay? Now this is the part. Round the significant to the number of bits, appropriate number of bits. Now we have to do something with this 1, 1, 1 that we have in the GRS. Okay? So go ahead.
If we did have to normalize, then would the G and R change too, or do we leave them the same?
No, GR change, but sticky doesn't change. So if you have to normalize shift things right and left, everything is shifted right and left, but the sticky remains 1. Okay. Now we have this 1, 1, 1 here. We should do something about it. We use this is where we use GRS. The entire point of having GRS was for this. What do we want to put for this bit here? Okay, because the default rounding scheme in IEEE 754 standard is round to nearest tied to even. We just round it to the nearest one. And that means that they have to have a 1 here. Okay? So I use GRS, round to nearest, this becomes 1. Okay? Now I can return this number to hexadecimal, and this is what I get. I can also find the floating point. Now, what if after this entire process of shifting right and left and so on, we had number 1, 0, 0 at GRS? Then what would happen? What would be this bit here? Blake is saying it can be a 1. Who agrees with him? Ian thinks it's going to be a 1 too. Anyone else?
I think it's like tied, right?
Sure. So then what's going to be?
I think it'd be 0.
So Xander thinks it's going to be 0. You also think it's going to be 0. And the right answer is 0. So it's 1, 0, 0 is a tie case. Then we look at the bit here. If it's an even number, we're not going to change it. If it was an odd number, then we have to add 1 to it. So if I had a 1 here, if, let's say I had this case, and my fraction was 0, 0, 1, and so on. If I had this, when I wanted to round it, I should have changed this one to 1, 0, 0. And so on. But that's an even case, we don't change it that much. Does it make sense? So I'm gonna ask about this in your exam probably, or quiz. Now I'm gonna give you some number. You have to deal with the rounding, GRS, shift left, shift right, do your thing, and round it at the end. Any questions? Cool. So know this. Now let's finish this module. So we do have floating point registers in MIPS. If you have used Mars, and by the way, how many of you guys have started the project? That's not a bad number. How many of you have finished the code? Okay, good, good. So if you look at Mars, Mars has, on the right side, we have the register file. We have integer registers, which are T, S, and so on. And then we also have a coprocessor register, which is floating point. Floating point registers start from F0 to F31. We have 32-bit registers that are reserved for floating point operations. Okay, so we do have floating point operations, arithmetic floating point add, single, and double precision. So this is the way it is shown. We have add.s, s is for single. We have add.d, is double precision. And this is how it works. If we have add.s, it adds, for example, F2, F4, F6. It adds F4 and F6 and put the results in F2. Okay? So we have floating point adder, floating point multiplier, single precision, double precision. We only have 32-bit registers. Now, the big question here is, double precision floating points need 64 bits. We only have single 32-bit registers. So can you guess what we do with double precision floating point numbers?
Combine two words.
We use two registers, right? We use two registers. So for that reason, when you use double precision add or subtraction or whatever, we only work with even registers. So we just say, use and add a double precision add, F4 and F6 and F2. So what it is really doing is adding F4 and F5 with F6 and F7 and putting result in F2 and F3. So we only work with even registers because the odd one after that is kept to deal with the 64-bit representation of a double precision floating point. Okay? So you can actually use double precision, but you need more registers. And then we have load and store, which is shown here. So you can load a floating point number, you can store a floating point number, and so on. So these are all R-type instructions. So when we were talking about R-type, we mentioned that the opcode is always going to be 0, and then we use function to find what kind of instruction we have. That's not always the case. If we have a floating point number, the opcode will be 0x11. And when you have R-type, you check that. When you see 0x11, you know that this is a floating point instruction. And after that point, it's going to be the same type. We are going to have the 5 bits for RS, 5 bits for RT, 5 bits for RT, shift amount, and so on. It's an R-type instruction, but we do have the opcode is going to change and function is going to change. So we have the opcode of 0x11 floating point, but then we have, for example, 0 for addition, 1 for subtraction, 2 for multiplication, 3 for division. And the interesting thing here is that we actually use, they also have their own numbers, the registers, to deal with that. So you can get more information about encoding here. I'm not going to ask a question about encoding floating point instructions. This is for your information. So you're not going to be asked to convert a floating point instruction to machine code, but you will use floating point instructions in your project. Okay? So now we're using integer multiplication, vector multiplication, dot product. Then you can test the floating point and see how that works.